Hello everyone, my name is Andrew Ragooch and I'm from the University of Waterloo, which is just outside of Toronto in Canada. It's with great pleasure that I'm presenting this talk today in the very first European Conference on Fracture. The focus of my talk will be a method for comparing the fatigue performance of forged magnesium components. I'd like to acknowledge the support of the funding agencies and industrial partners who made this work possible. This particular presentation is detailing the nuances of developing a comparison method for fatigue performance of forged AZ80 magnesium alloy, but it's part of a larger project where we actually designed, analyzed, optimized, and manufactured automotive suspension components from magnesium for vehicle lightweighting initiatives. So this presentation will aim to summarize a holistic approach we adopted in this research project known as the Integrated Computational Materials Engineering, or ICME approach, which is an approach to design products and the materials that comprise them and their associated processing methods via linking the material models at multiple length scales. You will see results from this talk spanning the full range of length scales illustrated in this diagram, but in general I'll focus on the micromechanics of the research and then gradually zoom out towards the system level to see how the process structure property performance relationship interacts with the knowledge development at each of these length scales. Somewhat of a prelude to the talk, I like to present this photo of the final component which was produced as part of this work, not only because it might be visually appealing, but to emphasize the main objective of the work, which was vehicle lightweighting. We targeted a fatigue critical automotive suspension component, which we were able to achieve a 37% reduction in mass versus the aluminum baseline component. This type of paradigm shifting improvement was only possible due to the experimental method which was adopted to optimize all facets of the research process. On the left-hand side of the slide, you can see a schematic of the forging process where intense pressure between rigid dies forces the material to flow in these internal cavities and conform to the desired component geometry. This can have many beneficial effects for fatigue and some detrimental ones if the process is not carefully managed. And this is done at moderate temperatures between 250 and 450 degrees Celsius. So the process being managed is a highly thermomechanical equation to satisfy. An overview of my talk can be divided into three sections. The first two deal with understanding the effect that the starting material has on the fatigue of the forged AZ80 magnesium alloy. The second is the effect of the most significant processing parameters being temperature, strain rate, geometry, lubrication, orientation within the die, etc., and how they play a role in the fatigue performance of the final component. And then finally, I'll follow up with a more detailed method of comparison using fatigue data that we've developed and characterized to understand how to design a forging process that will result in a desirable component with desirable fatigue properties, and then understand the variability that's associated with forging real components. So now that was a lot of information regarding how we went about the project. However, to summarize and better understand the structure-property relationship, I've distilled all of those phenomena that I previously discussed down into a few key elements. Firstly, the obvious comparison of what is the difference between the starting the forging process development with a cast or extruded material. On the left, you can see the monotonic tensile response of the as cast and the as extruded material. AZ80 is the alloy here of magnesium in all the different material directions. You can observe that the cast material has identical material properties in all three directions, differing from the extruded material, which has anisotropic behavior. You can see that in the varying material responses here in the two different directions. Furthermore, there's an obvious difference between the two, with the extruded material having a much higher strength and enhanced ductility, which is typical of rod forms of magnesium alloys. Secondly, these observations are supported by the comparatively higher superficial hardness that's shown in these contour plots on the right here of the extruded material once forged. These are shown on the same 30-ton Rockwell scale here. Due to the complex cross-sectional nature of these forgings that were investigated, there's a pronounced spatial variation in the properties. So this is a topic I'll discuss in more detail. These are just I-beam intermediate type forgings here. It's not a full component scale forging, but I will be discussing that towards the end of the presentation. Now, extending this comparison towards the fatigue performance of cast and extruded AZ80 magnesium As one might expect, there's again a dramatic difference between the two, as was indicated in the tensile monotonic curves, which is deeply rooted in these contrasting microstructures between the two, the different textures, leading to vastly different material responses and cyclic responses. It can be observed that under strain control fatigue testing, in the high cycle regime especially, for a given strain amplitude, the extruded material has a life which is superior to the cast material by a factor of more than 10, or an order of magnitude. Now, the second phenomenon which I'd like to discuss is the effect of forging temperature on the monotonic behavior, which is by far the most significant process parameter. You can observe that in general, higher temperatures have enhanced ductility, as we can see in the images on the right here. However, at the cost of lower strengths. Furthermore, the increase in material properties is obvious between the as received and the forged materials. So the forged materials generally are indicated by the colored lines, and the as received are the black lines. Linking that back to a previous observation, the superficial hardness correlates well with the yield strength of the material in various locations throughout the cross-section of the forging. As you can see, location B generally has the highest yield strength, which is this center region that has the highest amount of strain due to forging, and it has the highest amount of superficial hardness. The other important observation is how the base material is modified due to forging. There's a much more pronounced improvement due to forging with the material when you start with as cast material, whereas the improvement with wrought material as the base material, being the extruded material, is more marginal, as one might expect. Once again, it can be observed that under stress control fatigue testing now, so a different method of comparison, in the high cycle regime, for a given stress amplitude, the extruded material has a life which is superior to the as cast material by more than 10 times, as you can see here. Important note is that the materials being compared are from a full-scale forged component, so the effect of the processing temperature is really the most important in the last step of the thermal history prior to the in-service use. So, i.e., this isn't the extrusion temperature of the material prior to forging, but it is the die forging temperature and the subsequent cooling schedule after forging that governs the final microstructure. Although we did look at a post-forging heat treatment in this particular project, I've chosen not to discuss them here as they're very alloy and application specific. So you can simply think of the analogy that the final heat treatment will govern the resulting microstructure, as it does in many materials that we utilize in engineering systems. Um, the precipitate content is also governed by this final heat treatment and the morphology of these precipitates, as well as the final properties. If no specific heat treatment is given, it's the last step of the thermal history during the forging process that effectively is replacing this heat treatment. So as you can imagine, the physical component is a complex three-dimensional shape as indicated here. So thus the local strain and thermal histories throughout the component can spatially vary. And we looked at characterizing all these different locations. So there was 18 different samples in these particular components to understand the spatial variation in more depth. So now overlaying all these individual data points that we've collected over the SN curve, one can easily appreciate that even at the component level of forging, a large amount of variability occurs in the properties, which is highly a function of the location within the forging itself. So indicated by all these numbers are all the different forging locations within this component. For reference, overlaid on the curve is a design curve, so that's these dashed lines here, for the benchmark aluminum, which is this dashed black line here, which we can see is easily exceeded by these two other forgings that were done. Only by the forging that was done at 300 degrees Celsius do we get a superior property, however. This provides confidence that if we get the forging parameters right and the process control right, we can meet or easily exceed the baseline performance in fatigue for this particular component being an A356 aluminum alloy. So now looking at the effect of forging design, so between all the different forgings that we've investigated, we've looked at a variety of different forging geometries and configurations. Here we can see a dramatic improvement in the fatigue performance of the as cast material once forged in a simple upsetting technique to produce these types of flat forgings here that do not restrict the material flow in either direction. So this is a substantial increase in material properties that's typical when forging cast varieties, as I previously discussed, of magnesium, which the benefit basically is coming from the refined equiaxed microstructure, which is resulting from the thermomechanical processing. However, when we look at the extruded and forged material, which was forged in a totally different configuration of forging now, which was this closed die I-beam type shape, the differences are not quite as simple. Since the starting material was wrought to begin with, there is a more modest modification of the properties due to forging. In general, an improvement is always observed in the high cycle regime, as seen here. However, at lower forging temperatures, limited ductility in the material might cause a small degradation in the strain control fatigue behavior, as we can see here. Finally, when we compare the strain life curve for all of the various styles of forging, we can observe that once again in the high cycle regime, the full scale component is actually superior to all of the other investigated conditions. This is critical as the majority of the loading history for this particular application in the service loading will be exercising this kind of mid to high cycle regime of the strain life curve. So we're particularly interested in that particular location of the strain life curve. So now, as one might think, simply because the final forging process is superior to the intermediate steps which we looked at, so the different styles of forging and the different temperatures and the different forging configurations and the different base materials, does it really mean that we've fully optimized this process from a holistic perspective? So I definitely would like to ask that question and say that it's a very excellent question. So now you might be asking yourself, is deciding upon a comparison method to optimize the forging technique really as easy as just looking at all the response curves that we were just looking at as what I previously discussed? Although some very powerful general conclusions can be drawn, the results which I showed really depended upon the method for which you choose to compare the different variables related to fatigue. So now if we keep that in mind, I'd like to move forward and discuss how to effectively compare the material behavior and quantify that variability. So for the first basis of comparison, it begins with the actual loading history for the application. So the loads will be realized as stresses and strains within the component at the material level. So the application is a automotive suspension control arm, as we can see here. So in order to simulate this type of real world behavior, we implement a variety of different laboratory style tests, which use fully reverse loading over a wide range of amplitudes to characterize the material behavior. As the vehicle undergoes kind of individual cycles within the fatigue block, as we can see here, the material is undergoing cyclic hysteresis as indicated by the loop on the right here. The first approach employed is to use the stress reversal as the basis here. So we can see that indicated at the top and bottom here for characterizing the fatigue life. So if we impose the minimum and maximum stresses as the boundary conditions for the experiment, then we measure the resultant material response. So the key output for this is an SN curve from this style of test. The second technique is to control the maximum and minimum strain amplitudes and measure the stress response of the material. So the key output from this style of test is a strain life curve, which is generally used to model the material behavior in the automotive domain. Finally, we can also use an energy quantity, so the strain energy density, as a basis for comparison. And by energy, effectively what I mean is the combination of the elastic or the reversible strain energy density signified by this gray triangular area on the right, and the plastic or irreversible strain energy density is signified by the yellow area enveloped within the hysteresis loop on the left. So now the argument can be made which technique is most representative of the actual loading in the service environment of the vehicle. And the answer is, well, it depends. I'll go through and discuss what these comparisons yield when looking at the full-scale control arm forging that we've discussed earlier and the conclusions that we can draw from the spatial variation in the properties within each. What you're looking at here is the first case. So it's a comparison technique by the method of stress control fatigue testing. So recall that the SN curve that I presented earlier with all the data points that were scattered around that's shown on the right here. So the design curve in the middle, which is shown by this equation here, represents kind of the average material behavior, with some locations on the control arm having a life which is above this kind of idealized response. So everything to the right of this curve here. So if we non-dimensionalize these data points with ones that fall to the left being kind of worse than the idealized response and ones that fall to the right being better, once we non-dimensionalize these relative quantities, we can effectively get a life multiplier that describes how much each location deviates from this idealized response. So these are the life multipliers here shown on the contour plot. we can then map these onto the various locations of the control arm and understand the spatial variation. It can be seen that in location 1, near this region of the line here, a location which is a topic of further discussion in another presentation actually in this virtual conference. It has the lowest life multiplier with a life that's over 4 times less than the idealized behavior. Whereas location 9 on the other side of the arm shows kind of the converse effect, where the design curve is conservative in its fatigue prediction. In general, these internal regions here, which are kind of the web regions of this I-beam of the control arm, between the flanges on the outward side of the arm, have kind of superior fatigue performance, as you can see here. Similarly, we can do the same thing for strain control fatigue test being the method of comparison, and we can draw a few more conclusions. Firstly, the contour plot scale here has been exaggerated to highlight any differences throughout the arm, but you can see that in general, when comparing the spatial variation using a strain control approach, the multipliers are much closer to a value of 0, indicating that the design curve more accurately represents the material location, which is a good thing when we're using this for fatigue life prediction. Important to note, however, is that the critical region, which was location 1 in the arm, as indicated in this image here, is still the region with the lowest multiplier or the most non-conservative prediction. This provides confidence that in the fact that both comparison methods that we've investigated so far indicate similar trends in the behavior. Finally, when comparing on an energy basis, the story is similar to the previous slide, where the contour level is even further exaggerated to highlight these differences in the spatial variation throughout the control arm. Any differences observed here are more closely linked to defects within the material, as the spatially varying thermomechanical history would manifest itself as a different level of cyclic strain energy density. So we can see a much closer representation of the design curve to all of the data points being very much not scattered or scattered very closely around it. So to summarize how one might select the optimum forging condition based on all of this information, we can utilize a number of metrics. Since the fatigue response is the focus here of this particular application, I'll discuss how varying the processing parameters affect the strain control fatigue response. The strain life curve presented here is for both forms of magnesium alloys, cast and extruded. Now we can recall that the extruded material is textured and will exhibit an asymmetric cyclic response. Accordingly, you can see this induces anisotropy in the fatigue life. In the strain life behavior as the curves vary between the extrusion and the radial direction for the exact same material. So that's important to note here, the ED and RD directions of the extruded material. Next, adding the as cast open die forged material curves, we can observe that the dramatic improvement being observed realized especially in this low cycle regime. So, but fairly much across the board. Finally, we can introduce the optimum forge condition that illustrates a very dramatic improvement over all the conditions, especially in the high cycle regime, a strain amplitude is less than 0.5, which once again is where we are desiring kind of high fatigue performance for this particular service loading. Finally, as a sanity check, benchmarking these responses against kind of the state-of-the-art material for these types of structural components, which is a 6082 T6 aluminum, we can observe that the forged material can meet or exceed kind of this baseline target for strain life behavior. Now, what you saw previously was just a snapshot of one form of comparison to evaluate which processing condition is optimal. Given the practical requirements of engineering application, an optimization function was developed that incorporates 3 different non-dimensional variables, which incorporates various aspects of the material characterization into one function whose objective is to maximize its value and obtain optimum performance. The first term, which is phi1 here, describes the necessity of the component to have a high strength and toughness, non-dimensionalizing these individual property attributes to have against the maximum observed over the wide range of processing conditions allows us to have a term which reaches a maximum value at a unity or a value of 1. The second term incorporates the fatigue behavior in terms of parameters extracted from an SN curve. Finally, since this is because fatigue, since fatigue is a defect-driven phenomenon, we can, which can be governed by the limiting location within the component that has the most inferior properties, as we illustrated in the previous slides. The spatial variation of the hardness of the component was also considered to ensure we selected a processing condition that produces a uniform component with uniform properties that are free of major defects. So now calculating the magnitude of this objective function shown up here for all the investigated processing conditions, and the following surface plot can be generated for as cast AZ80 magnesium and as extruded AZ80 magnesium that was then later forged for both cases. Once again, a value of 1 on this surface is technically considered to be optimal. So we have strain rate on one axis, forging temperature on another axis, and optimization parameter on the z-axis, which is effectively representing how optimal that particular forging condition is. So selecting an optimum condition here would be the extruded and forged material process at 250 degrees Celsius and a strain rate as fast as pragmatically possible of 10 per second. Important to note here is the fact that the weight factors that have been selected here, so these coefficients, were specifically tuned for this engineering application that we've considered here, but effectively can be retuned to meet the requirements of other structural components. Finally, if we impose some constraints upon this optimization surface, such as the fact that at the extremities of very low temperatures and high strain rates, we observe cracking defects, as you can see here within the material. Secondly, at temperatures that exceed 426 degrees Celsius, which is including the heat of deformation, that's the incipient melting temperature of the material, and that can result in inferior properties. So we might exclude that region from the processing domain as well. Finally, the practical constraint of forging press loads can prevent forging at a very low temperature, even at comparatively low strain rates, just because we run out of, it's not pragmatic to forge at such high loads. This effectively limits our processing window and generally will constrain the optimum forging condition to be a compromise of all these pragmatic conditions. So you can see how the optimum forging condition will move from this location here to slightly here once we impose the constraints. Furthermore, although not very significant in AZ80 magnesium, the cost differential between as cast and as extruded forms of base material might make another option seem more attractive if cost saving is can justify the degradation of performance that's typically realized with starting with cast starting microstructure. So some concluding remarks: a stress, strain, and energy-based fatigue approach were used as a basis for comparison of the durability performance of forged AZ80 magnesium components. Secondly, the optimum processing conditions which lead to the most desirable fatigue properties are highly dependent on the in-service application that's being utilized or that the component's being designed for. Finally, an optimization function was developed for an automotive fatigue critical component, which was utilized to select forging process parameters which result in optimal performance. And with that, I'd like to thank you for your attention and open the floor to the audience for any questions. In closing, I'd like to challenge the audience to tell me a concern that they may have as researchers towards using magnesium as a material for fatigue critical components. I would very much like to collaborate. Here are my contact information at the bottom here, and I very much appreciate the opportunity to collaborate in this online medium and this virtual conference. Very much thanks, and thank you again.
AZ80 magnesium components by Dr. Graiguk.
Hi, thank you.
Graiguk, yes, the floor is yours.
Thank you very much. I'd like to extend my thanks for graciously to the session chairman for graciously allowing me to join this particular session. Hopefully you can see my screen now.
Yes, we can see. We can see very clearly.
I'm actually from the University of Waterloo in Canada, so the time zone difference made it difficult for me to present in another session. So I graciously thank you. Just a brief overview of the research work that was done. We investigated doing characterization campaign as well as understanding kind of the simulation and the physical process development of forging of magnesium. So we completed a campaign where we simulated the forging process and we forged physical components. You can see an example here. We achieved a 37% mass reduction versus baseline. The target was an automotive fatigue critical component. Some of the things that we looked at in terms of the process optimization, the effect of the starting material, if we started with a cast microstructure material, an extruded microstructure material, the effect of some of the pre and post treatments. As far as the process goes, we looked at the sensitivity of the fatigue properties to the forging temperature, the forging strain rate, the component geometry and the forging die geometry, and how the progressive steps of forging actually occurred, the lubrication and the orientation of the material. And then kind of this most important part of the talk is how we can compare fatigue properties for optimizing this forging process. So for a basis of comparison, we looked at utilizing the in-service loading from a stress-based perspective, and we compared the fatigue properties to develop the optimum forging process based on that. We also looked at a strain-based perspective and an energy-based perspective, and then we developed kind of this this model here that we can effectively describe the spatial variation throughout the forging itself of the fatigue properties, because the thermomechanical history varies throughout the entire forging, because the amount of thermomechanical work and the temperature history varies. The ending microstructure and the ending texture is different throughout the forging. So that affects the cyclic damage mechanisms, and it also affects the strength locally in each of these areas. So from a stress perspective, we had certain areas that had a higher property and a lower property. From a strain comparison perspective, we had areas that were very similar. And an energy-based perspective, it effectively allowed us to compare in a very accurate way. We also developed an optimization function. You can see it's a very simplistic function with just 3 terms. Each term, one kind of captures the strength, one captures the fatigue behavior, and one captures the homogeneity of the properties. Graphing these terms on a surface, we can see that the optimization parameter for a given strain rate and forging temperature, that's the X and Y axes of this 3-dimensional surface plot. We can see that we determined an optimum forging condition to be 250 degrees Celsius using extruded material at 10 per second forging rate. And with that, I'd like to take any questions. I thank you for your time.
Thank you, Dr. Greigug, for your very concise presentation, very interesting talk regarding fatigue and which parameters affect the fatigue life of such critical components. And now we open this talk for discussion, and we remain for any additional question regarding this presentation.
I have a question.
Yes, please.
Okay. Would it be fair if I conclude from your final graph that increasing the forging temperature and reducing the strain rate creates the better condition? So do you expect that after forging you would have some residual stresses?
Excellent question, Casper. I guess I can just elaborate a little bit. The higher values here of the optimization parameter are what is optimal. So that's a lower forging temperature and a higher forging rate. With regards to residual stresses, we did actually measure those. Depending on the forging temperature, you could annihilate all of the induced twinning that is a result of the forging process, because we're utilizing magnesium. That's a very well-known deformation mode. Depending on that temperature, we virtually, pretty much for all of the temperatures we've investigated, you relax away all of the residual stresses. So there's nothing that remains, but you do retain the texture that was developed throughout the forging process. So the grain orientation is something that you retain, but the residual stresses is something that gets annihilated. Excellent question, though.
Thank you. And I see now that I didn't look properly. It's the lowest forging temperature.
Correct. Yes. Yep.
So thank you for your answer. Any additional question?
Yeah, I have a question.
Yes.
So in the previous slides where you looked at the fatigue properties on different spots on your final part, were those experimentally validated as well, or is this purely simulation?
Both. So we had a digital twin of the actual process. These are experimental results you're looking at here. And in the finite element simulation, we use the variable material property approach to actually mimic the degraded properties we're achieving in certain locations.
Okay, cool. Thanks. Very nice work.
Thank you. Any additional question?
Yes, hello. Here
Hello.
from the University of Cantabria. I have just curiosity about the how did you test the samples in fatigue? I imagine that you use that instrument machine that is in the presentation picture at the beginning. But how did you assure the axiality of the samples? Because as far as I see, they are not very big. They are quite small samples, 50 or 60 millimeters in length. So you have to be really meticulous in order to well not to have any disalignment. Or how did you do that?
Excellent question. We used a combination of control methods to actually control the test using Instron and MTS servo hydraulic control machines. The samples, because the components are quite small, as you noticed, the samples are 60 millimeters or so in length, just to fit inside the component and achieve a large number, so we can kind of get a representative nature of the spatial variation in the properties. But we do align the fixtures very regularly so that we're achieving kind of a pure strain state. One of the focuses of another talk that I'm doing tomorrow is on the multi-axial nature of the fatigue. So this is only uniaxial data you're seeing here, but we have done multi-axial tests with a different sample type.
Yes, but I mean, in order to assure the axiality, perfect axiality, did you use any kind of element that was impinging the moments, or did you just use any kind of laser tool in order to fit it really straight?
Okay, excellent. I understand your question now. We use digital image correlation to I guess monitor the out of plane movement of the actual face of the sample. The samples are precisely machined, and we can monitor any eccentricity in the loading as a result of that.
Okay. The question was that. Okay, thank you. Thanks a lot.
Thank you. I have one question, if you allow me, and
Of course,
before
yes.
closing this, yes, before closing this presentation, and regarding this graph in design curve, this is based on Coffin-Manson law concerning the strain life. So do you consider to use, because I see that you have a high cycle fatigue life. I mean, above 100 cycles, you can consider that maybe stress life approach could be usable in this case?
Excellent question. So that's kind of the focus of the full length video presentation. What you're looking at here is a Coffin-Manson type equation, but it's using energy-based results. So based on this particular plot here, this is using stress-based approach, which doesn't capture the compressive reversal very well with magnesium because of the twinning that is the damage mechanism, because the material is so asymmetric in its cyclic response. So this is the stress-based curve. When we use strain-based data, experimental data, this is what it looks like. And when we use energy-based data, this is what it looks like. So the paper actually compares all three methods and their validity with respect to capturing accurately the fatigue life predictions. Energy-based approaches work the best. Stress also work, but they're not as accurate.
And how many replicates do you have for its, let's say, strain amplitude? How many replicates to make this curve?
Excellent question. So with each component, we were able to extract 18 samples from, and we did different types of fatigue testing. So we had, I think, 10 or 15 components in total. At each strain amplitude, in general, we had at least 2 replicates, sometimes 3. So we can see,
okay.
Yes.
Okay. Thank you. It is very nice and very comprehensive work. Well done.
Thank you very much.